Ever wondered how doctors can peer inside your body without cutting you open? Traditional imaging methods like X-rays or MRIs have revolutionized medicine, but there's a new player on the scene: microwave tomography. This cutting-edge technique uses microwaves to map the electrical properties of tissues, offering a non-invasive, low-cost alternative to PET scans. But here's the catch: reconstructing those images is like solving a puzzle with missing pieces. The math is super tricky, and tiny errors can blow up into big problems. Let's break it down. Microwave tomography works by sending microwave signals through the body and measuring how they scatter. These scattered signals hold clues about the tissue's electrical properties, like whether a tumor is hiding in there. But here's the challenge: the equations governing this process are nonlinear and ill-posed. Think of it like trying to reverse engineer a recipe from a burnt cake. Small changes in the ingredients, or in this case, the tissue's properties, can create wildly different results, and there's often no single right answer. Traditional methods try to tackle this by simplifying the math, but that usually means losing fine details, like missing the forest for the trees. Deep learning has stepped in, using neural networks to predict images from data. But here's the problem: these models need massive datasets of paired examples, like thousands of scans with known outcomes, to train properly. And even then, they struggle when conditions change, like different sensor setups or tissue types. So how do we fix this? Enter learned regularization, a clever twist on old ideas. Imagine you're painting a portrait, but instead of starting from scratch, you have a set of brushstroke patterns that usually look good. These patterns, or priors, guide your painting without dictating every detail. In this research, scientists use diffusion models, the same tech that powers AI art tools, to create these priors. But here's the kicker: they didn't need paired training data. Instead, the model learned from the physics of microwaves themselves, embedding realistic anatomical structures directly into the reconstruction process. The result? A method called SSD-Reg, that's like a supercharged version of traditional techniques. It's stable, accurate, and adaptable. No more relying on huge datasets or guesswork. By blending physical laws with machine learning, this approach could revolutionize how we detect tumors, monitor strokes, or diagnose skin cancer, all without the radiation of PET scans or the invasiveness of biopsies. So the next time you hear about AI in healthcare, remember, it's not just about flashy algorithms. It's about solving real-world puzzles, one microwave pulse at a time.